Watch this flower bloom, fully animated in Java Swing. Smooth motion, vibrant colors, and real-time growth, all coded from scratch. Let's bring this flower to life. Let's start by creating a new class called Blooming Flower. We'll begin by adding the import statements needed for our animation. Swing gives us access to JFrame and JPanel so we can build the window. From out, we bring in the basic graphics classes like color, graphics, and rendering hints. Next, event lets us handle keyboard input and timers for smooth animation control. Finally, geom provides powerful geometric shapes, like ellipse 2D and curves, which we'll use to draw the petals, stem, and leaves of our flower. These imports set the foundation for our Blooming Flower class. Our class extends JPanel to create a custom drawing surface, and it implements Action Listener for timer updates and Key Listener so we can control the animation with the keyboard. Since we're using Action Listener and Key Listener, we need to implement all their abstract methods. That includes action performed for handling timer updates, and the 3 key methods, key pressed, key released, and key typed, so our program can respond to keyboard input. Next, we declare our variables. A timer to drive the animation, a paused flag to let us stop and resume, and a t-value to track the progress of the bloom. Finally, TD controls how fast time advances. Here it's set so the flower takes about 6 seconds to fully bloom. Now we define the visual style of our flower. We'll start with an integer for the number of petals, set to 10 by default. Then we pick colors, a vibrant pink for the petals, with a lighter pink along the edges to give them depth. The center uses a warm yellow to stand out. For the stem, we choose a darker green to feel sturdy, and the leaves get a brighter green for balance. These color settings make the flower look lively and natural, and you can easily adjust them to experiment with different designs. In our Blooming Flower constructor, we prepare the canvas for animation. First, we set the preferred size to 900 by 900 pixels, giving plenty of room for the flower to grow. The background is a dark bluish color so the bright petals and leaves will really stand out. We then make the panel focusable and attach a key listener, which allows us to pause, restart, or save the animation using the keyboard. After that, we create a timer that ticks 60 times per second, ensuring smooth motion, and finally we start the timer so the animation begins right away. We first check if the animation is not paused. If it's running, we increase the value of t, which represents the bloom progress. To keep it within range, we cap it at 1 using math.min. This makes sure the flower only grows until it's fully bloomed. Finally, we call repaint, which redraws the panel with the new state of the animation. Here we add an easeout cubic method. It takes a value between 0 and 1, and returns a smoother curve using a cubic equation. Instead of the bloom opening at a constant speed, this easing makes it start quickly and then slow down near the end, giving the flower a more natural feel. Next, we add an ease in out cubic function. This one creates a smooth acceleration and deceleration effect. When x is less than 0.5, it eases in, starting gently. After that, it eases out, slowing down toward the end. We'll use this for parts of the bloom where we want the motion to feel natural and balanced on both sides. Now we add a helper function called lerp, short for linear interpolation. It takes a start value, an end value, and a fraction t. As t goes from 0 to 1, this method smoothly blends between a and b. We'll use it to animate sizes and positions of our flower elements over time. Next, we add a clamp function. This makes sure any value stays between 0 and 1. If x goes below 0, it returns 0, and if it goes above 1, it returns 1. This is especially useful for keeping our animation progress within safe limits. Now we're going to design the shape of a single flower petal. We'll create a new method called petal shape, which takes two parameters, the length and width of the petal. These will let us easily scale and reuse the same petal for different sizes later on. Inside the method, we store those parameters in local variables L and W, just to keep the code clean and readable. Next, we create a new Path2D object. This class gives us full control to draw smooth, curved shapes, perfect for natural forms like petals. We start the path at the origin point, using move to 0, 0. That's the base of our petal where it connects to the flower center. Then, using curve 2, we define the first smooth curve, moving out to the right, slightly upward. The control points use the petal width and a fraction of the length to create a gentle outward bend. The second curve continues that motion, rising up to the very top of the petal. This forms the outer contour, a soft, organic curve that gives the petal its natural shape. Next, we mirror that motion on the left side, using negative values for the width. That brings the curve back down symmetrically toward the base, completing the left edge. Finally, we call close path to connect the end back to the starting point, creating a sealed shape that can be filled or shaded with color. By returning this Path2D object, the method gives us a clean, symmetrical petal we can rotate and reuse around the flower's center to form a full bloom. Next, we'll add a subtle detail to bring our petals to life, the highlight. We're creating a new method named petal highlight, which, just like before, takes the petal's length and width as inputs. Inside, we start by creating a new Path2D object to define our highlight shape. Then we shorten the overall length by multiplying it by 0.75. This ensures the highlight sits neatly inside the petal instead of stretching all the way to the tip. We begin the path a little below the top with move to 0, L 0.15, and then use the first curve to command to draw a smooth line curving gently to the right side. The control points are scaled by the petal's width so the curve hugs the inner edge naturally. Next, we mirror that curve to the left using negative width values. This forms a balanced, leaf-like highlight that follows the inner contour of the petal. Finally, close path seals the shape so it can be filled with a soft, light color. When rendered, this inner layer catches a bit of light and adds depth, giving each petal a glossy, three-dimensional look instead of a flat color. By combining this highlight shape with the main petal, our flower gains that polished, lifelike glow that makes the bloom feel organic and real. It's a small touch, but it adds a huge difference in realism and visual appeal. Now it's time to design the leaf, a simple but elegant shape that completes our flower. We'll create a new method named leaf shape, which takes two parameters, length and width, allowing us to control the leaf size dynamically. Inside the method, we start by creating a Path 2D object to draw the outline. Then we move the drawing cursor to the base point at the origin using Move to 0, 0. From there, we use our first curve to command to draw a smooth arc outward to the right. The control points define how far the curve bends and how sharp or gentle the tip becomes. We guide the curve up toward the top using the length variable, forming one half of the leaf's contour. Next, we mirror that curve on the left side, using negative width values to keep it perfectly symmetrical. This gives the leaf its classic, balanced shape, narrow near the stem and slightly pointed at the tip. Finally, we call close path to seal the outline, turning it into a complete, fillable shape. When rendered with gradients and a subtle outline, this curve captures the natural softness of a real leaf. Even though the code looks simple, these few lines create a beautiful, organic form. Later, we'll rotate and position several of these along the stem, so the flower feels alive and connected to nature. Now we're adding a small but powerful helper function called point_on_quad. This method helps us calculate a precise position along a smooth, curved line, also known as a quadratic Bézier curve. It takes two inputs, the curve itself and a parameter t, which goes from 0 to 1. Think of t as a slider that moves from the start of the curve to the end, letting us find any exact point in between. Inside the method, we use the Bézier curve formula to calculate both the x and y coordinates. The math might look complex, but it's really just a weighted blend between the curve's start point, control point, and end point. When t is 0, we get the first anchor point, when t is 1, we reach the end, and everything in between gives us a perfectly smooth transition along the path. Finally, we return a new point2D object containing those coordinates. This tiny function becomes extremely useful for our animation. It lets us find the exact spot along the curved stem where a leaf should grow or where a petal might attach. Next, we'll add another essential helper method called tangent_on_quad. While the previous function gave us a position on the curve, this one tells us the direction the curve is facing at that exact point, also known as its tangent. It takes the same two inputs, a quad curve 2D object and a parameter t that runs from 0 to 1. Inside, we use the derivative of the Bézier formula to find how the curve changes at that point. For both x and y, we calculate the difference between the control point and the start, and between the endpoint and the control point. These values are scaled by 1, t, and t, giving us the slope of the curve's path. Once we have those x and y components, we return them as a point2D, which represents a directional vector, not just a point on the screen, but the exact orientation of the curve at that spot. This direction is incredibly useful in animation. We'll use it to rotate the leaves and petals so they grow perfectly aligned with the curve of the stem, giving the flower a natural, flowing structure instead of rigid, flat placement. Together, point-on-quad and tangent-on-quad form the mathematical backbone of our organic animation. Now it's time to bring our leaf to life. We're creating a method called drawLeaf, which will take care of positioning, rotating, coloring, and drawing each leaf along the flower's curved stem. This function receives several parameters: the graphics 2D object used for drawing, the stem curve itself, a value called D on stem to decide where along the stem the leaf appears, a side indicator that determines whether it grows on the left or the right, and finally appear, which controls how much the leaf has grown in the animation. Inside the method, we start by storing T on stem into a local variable named U, just to keep things readable. Then, using our helper function point-on-quad, we find the exact position on the stem's curve that corresponds to this value of T. This gives us a precise coordinate point where the leaf should be attached. Next, we call tangent-on-quad to calculate the curve's direction at that same point. This tells us the angle at which the stem is bending, which we'll use to make sure the leaf grows in the correct orientation, naturally following the curve rather than sticking out at a random angle. We then use math.tatan2 to convert that directional vector into an angle, measured in radians. Since leaves sprout out to the sides, we rotate it 90 degrees away from the stem using -π/2. And to make the left and right sides alternate, we add or subtract about 28 degrees, depending on which side this leaf belongs to. Next, we define how big the leaf should be. We use our lerp and easeout cubic functions to make the size grow smoothly as the appear value increases. The length starts at 10 and expands up to 60, while the width grows from 4 to 26. This creates a gradual, natural unfolding effect, as if the leaf is slowly stretching out into the sunlight. Once we have the dimensions, we call our leaf shape method to generate the curved outline for the leaf. At this point, we know where to place it, how large it is, and the angle it should face. Now we use an affine transform to move and rotate the leaf into the right position. We first translate the shape to the point along the stem where it belongs, then rotate it by the angle we just calculated. This transform ensures that no matter where the stem bends, the leaf will always follow its flow perfectly. Next comes the fun part, coloring. We set a gradient paint from top to bottom, starting with a bright green and fading into a darker shade toward the tip. This gives the leaf a natural highlight and shadow, making it feel soft, alive, and three-dimensional. Then, using fill, we render the transformed shape directly onto the screen. As the animation runs, each frame draws a slightly larger version, creating the illusion of growth. Finally, we switch to a semi-transparent black color, reduce the stroke width to a fine line, and use draw to trace the leaf's outline.
That small detail adds contrast, helps define the edges, and separates the leaf from the background and stem. It's a perfect example of how math, art, and programming come together, where simple geometry and easing functions combine to form something that looks truly organic.
Now we're moving on to one of the most important parts of this project, the paint component method. This is where all of the visual elements of our blooming flower are drawn to the screen. Inside the paint component method, we first call super.paintComponentG to clear the screen before drawing the next frame. Then we create a graphics 2D object using g.create, giving us access to advanced drawing features like curves, gradients, and transformations. Finally, we enable anti-aliasing to smooth out the edges of every shape and line. These few steps prepare a clean, high-quality canvas, ready for us to paint the flower with soft, polished visuals. Next, We get the current width and height of the panel using getWidth and getHeight. These values make our drawing responsive to the window size. Then we calculate the center coordinates, cx for the middle of the panel, and size slightly lower, around 65% of the height. Now we create a smooth background gradient to represent the sky. We use a gradient paint that fades from a deep bluish tone at the top to a slightly lighter shade near the bottom. After setting this gradient as our paint, we fill the entire panel with a rectangle using Fill Rect. This gives our scene a calm, atmospheric backdrop that makes the flower colors stand out beautifully. Next, we draw the ground beneath the flower. We set another gradient paint, this time shifting from a rich green near the top to a darker forest shade at the bottom. Then, using Fill Rect, we paint this gradient starting from the flower's base all the way to the bottom of the panel. It creates a soft transition between the soil and the background, grounding the entire scene naturally. Here we add a gentle motion to the flower using a variable called sway. Once the bloom is fully open, it calculates a small oscillation with a sine function, based on real time from system.nanotime. We multiply it by a few radians to create a soft 3-degree swing, giving the flower a natural, lifelike movement, as if it's swaying gently in the breeze. Next, we calculate the length and position of the stem. Using lerp and our easing function, the stem smoothly grows from 40 to 260 pixels long as the animation progresses. We start at the flower's base, using cx and psi as the anchor point, then determine the tip coordinates. A touch of sine motion from the sway value makes the stem gently bend with the wind, giving the entire plant a soft, natural movement.
Now we draw the stem itself. We start by setting a thick, smooth stroke with rounded edges so the stem looks soft and natural. Then we set the drawing color to our stem color, a rich green tone. Using a quad curve 2D, we draw a graceful curved line from the base of the flower to its tip, with a slight bend to one side. This gentle curve gives the stem a realistic, organic flow, as if it's leaning naturally under the flower's weight. Next, We control when the leaves appear. We calculate a value called leafed, which starts growing once the main stem has partially finished. By clamping it between 0 and 1, we make sure it stays within a smooth range. Then, if the value is greater than 0, we call the draw leaf method twice, one on the right side of the stem, and another slightly higher on the left. Each leaf unfolds gradually, timed perfectly with the stem's growth, giving the plant a balanced, natural rhythm. Now we move to the top of the stem, where the flower begins to bloom. We store the tip position in fx and phi. This is the exact center of the blossom. At this point, we calculate how much the flower has opened. We use an easing function called ease in out cubic, which makes the motion start slowly, speed up in the middle, and then gently slow again as it finishes. This value, stored in open, controls how the petals unfold. Then, using lerp, we smoothly increase the petal length from 25 to 120 pixels, and the width from 6 to 60. Together, these lines define the graceful, natural opening of each petal as the bloom comes to life.
Now it's time to bring the bloom to life by drawing each petal in a circular arrangement around the flower's center. We start a loop that runs through every petal, using the variable I to track the position of each one. For each step, we calculate an angle A, which evenly spaces the petals around a full circle, using 2 pi divided by the total number of petals. We also add a bit of movement from the sway variable, which makes the flower feel alive, as if it's gently breathing or shifting in a soft breeze. Next, we create a new petal shape using the current length and width values we calculated earlier. Then we set up an affine transform, a powerful tool that lets us move and rotate shapes in 2D space. First, we translate the coordinate system to the flower's center, at fx and phi. Then we rotate the petal by its unique angle, making sure each one points outward in the correct direction. After that, we apply a small translation upward, which uses the open value to determine how tightly the petals are clustered. When the bloom is closed, the petals overlap near the middle. As it opens, they gently separate, revealing the full shape of the flower. Once the transformation is ready, we create the transformed shape, which gives us the exact final position of the petal on the screen. Then, we apply a radial gradient paint, starting with a lighter edge color that softly fades into a deeper tone toward the center. This gradient adds richness and a subtle glow to each petal, giving the flower a more realistic and dimensional look. Finally, we fill the transformed shape to render the petal. As the loop repeats for all petals, we gradually build a complete, symmetrical bloom, each petal curving gracefully outward, shimmering with color, and moving ever so slightly with the wind. This part of the code truly brings the flower to life on screen. With all the petals in place, we now draw the center of the flower, the part that ties everything together. We begin by calculating center, the radius of the flower's core. Using our lerp function, it smoothly transitions from 24 down to 18 pixels as the bloom opens. This subtle shrinking effect makes the center appear to tighten slightly, giving the animation a sense of depth and realism. Next, we create a radial gradient paint centered at the same point as the flower, fx and phi. The gradient moves from a brighter shade of the center color in the middle to a darker tone at the edges. This soft blend of light and shadow helps the center feel spherical, as if it's catching light from above. Finally, we draw and fill an ellipse 2D using the calculated radius. By subtracting the radius from both the x and y positions, we ensure the circle stays perfectly centered. Once it's filled, this golden core glows gently at the heart of the bloom, completing the main structure of the flower. It's a small but essential touch that makes the entire animation feel balanced and alive. Before adding the highlights, we lower the drawing opacity using alpha composite. Here we set the transparency level to 0, 15, or 15% visibility. This makes anything we draw next appear soft and subtle, perfect for highlights or glow effects. Now let's add a soft highlight layer to our petals. To do this, we'll reuse the same loop we created earlier for drawing the petals. Go ahead and copy the entire petal drawing loop from above. Once it's pasted, we'll make a few small but important changes. First, replace the method call petal shape with petal highlight. This will draw the smaller inner highlight shape we created earlier instead of the full petal. Next, remove these two lines from inside the loop. G2, set color, white, and G2, fill at, create transform shape petal. This will draw each highlight shape in white with a transparent overlay, thanks to the alpha composite we set earlier. The result is a soft shimmer across the petals, subtle but powerful, giving the flower a gentle glow and a sense of realistic lighting. Next, we'll add keyboard control to make our animation interactive. Inside the key pressed method, we use a switch statement to check which key the user has pressed. The first case listens for the space bar. When it's pressed, we simply flip the paused variable. If the animation is running, it pauses. If it's paused, it resumes. This makes it easy to stop and admire a single frame of the bloom or continue watching it unfold smoothly. The next case listens for the R key. Pressing R resets the animation by setting T back to 0 and unpausing the timer. This instantly restarts the bloom from the beginning, letting you replay the full animation as many times as you like without restarting the program. By using this simple key handling setup, we give the user direct control to pause, resume, or restart, making the project feel more dynamic and interactive. Finally, we set up the main method, the entry point of our program. Here, we use swing utilities.invoke later to make sure all the user interface code runs safely on the event dispatch thread, which is the proper way to start a swing application. Inside, we create a new JFrame titled Blooming Flower, Java Swing. This window will be the canvas that displays our animation. We set the close operation to exit _ close, so the program shuts down cleanly when the user closes the window. Next, we make the frame non-resizable to keep the animation proportions consistent, and then we add a new instance of our blooming flower panel as the content. By calling pack, the frame automatically adjusts to the preferred size we defined earlier, ensuring everything fits perfectly. We then use set location relative to null to center the window on the screen, and finally call set visible true to bring the animation to life. Once this method runs, the timer inside our blooming flower class begins ticking, and the entire blooming sequence starts, petals opening, leaves growing, and the flower coming alive right before your eyes. And there it is, our blooming flower, created entirely in Java Swing. Every petal, leaf, and curve is drawn through code, growing smoothly frame by frame. Let's restart it one more time and watch the full animation, from the first sprout to a fully bloomed flower. A perfect blend of math, color, and creativity, all powered by Java.